Yeah, for sure. Okay, well, I'll ask about it later if we have time. But so the stream is running now, and if you want to test it, let me see. I will send you a. I'll send you a link um, to test it, and then this will be the same link as the video later. So it's all in one go. It should stream live. If you weren't here with me, if you were like some other student studying for the exam that was invited to listen in, you could join this live share link, and then you could type in questions, but you wouldn't be able to join. You wouldn't be able to ask questions back or participate. You can do it because you're on the Zoom call. And let's see. Well, let me see why this screen share isn't working. It says window capture. I want display capture. Okay. So if either of us go to that link, we should be able to see and click
Did you send
play.
it out?
Capture. I want display capture. Okay. So it's working for me, and I'll try typing something into the chat.
So that link is.
And I'll try typing something into the chat.
Can you hear me?
Yeah, I can hear you.
Okay.
Did that link work?
Yeah. So that link is. Oh, that's kind of cool. There's a little bit of a delay too.
Yeah, well, it has to upload to the internet, and I'm going to go ahead and change the title to be correct. And I'll add it to playlist. And okay, so this should be the same link. Like as soon as the broadcast is over, probably like within minutes, it should finish processing, because I think it's processing throughout the streaming. Then you should use the same link after the lesson to catch up on everything we've talked about. So you don't have to keep it open. In fact, if you do, there might be echoes, but I just wanted to check that it's both running on our end. And then yeah, I will enable screen sharing, and we can jump in even to the homework. We can go over sort of all the material from last time leading up to it as well. But share your screen when you're ready, and I'm also going to grab my charger because I fear that it's not gonna last the whole hour.
All right. I'll wait for you to grab your charger to start. Oh,
Okay. Hit me. What's up? Where would you like to
Right.
start?
Um, we'll start with number one. It says to write the mystery gate as a Boolean logic formula. Um, using and, nots in a and or and not in a Verilog clock synchronous module.
Yes, an example of that is at the top of that page 20, looks like 208 or 206. So there's a bunch of writing on top of it, so it's distracting. So you can just go straight to the handbook. Look at a fresh copy of that page, and then also like know where it is. So you should definitely practice it a few more times, because when you're taking the test, you'll want to be familiar with the Verilog and not spend time sort of like
Yeah.
trying to figure out where everything is.
So I guess so if I'm understanding this correctly, what the question is to write a Boolean logic formula for this mystery gate right here, right?
When that mystery gate is the same as the one that we drew at the top of this page, so where you see the gates for A, B, C, D, E going into an output.
Okay, because I thought we did that one already. Isn't that what this is?
We drew it as a tree and then as a circuit, and those are the same. So the circuit is going from left to right, like inputs on the left to a single output on the right. And then if you just turn it on its side, it's a data structure called a tree, which
Uh-huh.
also has all the inputs as leaves, which are nodes that have no other children, and then has a single output, which is at the root, which is the the same as the node that has no parent.
Uh-huh.
So those are two equivalent forms. Now the question is to write a third equivalent form, which is Verilog source code, which looks like underneath where you're seeing there at the top of that page
Yeah.
in the handbook, it says modules Verilog. So that's an example of a module. They call it silly function, but ours, you can call it mystery gate. So your job
Yeah.
is to write a function like that, but for the two equivalent forms that we've already drawn. So remember at the very first lesson, there were, we talked about truth tables, we talked about gates, and we talked about this Boolean logic formulas, and they were all equivalent to each other. And so I had you practice, it's given one, translate it to another. And then over time, you saw that they were the same, and you could move back and forth. So no matter which two I gave you or which one I gave you, you could always translate it to another one. So this is
Okay.
the same. So these are equivalent representations of the same logic circuit. And in fact, if I asked you to write a truth table just for the sequential part, like the asynchronous logic part, here on the left, let me just request remote control just to point. So if I asked you to, just for this sequential logic part, so remember we talked about the two kinds of gates. There's sequential or combinational or asynchronous or unclocked. So that's these gates which don't have a clock circuit or a clock input. You can write a truth table for this, and you can also write, excuse me, I'm also getting over the flu, so
Yeah, sure.
that was the other reason why I was slow this weekend. I was kind of out of it. So this is a gate, and you can write a truth table for it, and you can also write Boolean logic for it in addition to this gate. And then what makes it different is that the Verilog now includes this clock part. So because it's a clock circuit, so even one gate that has a clock input that's synchronous makes the whole circuit a clocked gate. So now it's not enough to write just the Boolean logic before. So it's not enough just to have this expression in here. Now you have to have an expression which looks like one of these, which says if on some edge of the clock, then do this, otherwise do that, and then to be able to handle like a reset gate. So part of problem one also is that when you write the Verilog module, you don't have to handle just the asynchronous parts like the A, B, C, D, E, because you know how to do that, or you could watch the first video and review how to do that. Now you have to handle what happens when you have a reset in the clock. And pretty much the only reason you have the reset in the clock here for the big mystery gate overall is because of this one register on the output up here, which has a clock and then also has a reset. So you can imagine that in this gate, that clock and reset pin is pretty much going straight to the register at the end, and it doesn't really interact. It doesn't have any connection or net with the AND gate or the OR, the inverter, or the XOR, or anything like that. Okay, so now is the task more clear?
Yeah, I guess I misunderstood. I was thinking that I could basically I wasn't sure if I should be coming up with my own logic or my own formula, Boolean logic for the mystery gate. I wasn't that when I was going back to the video, I was trying to understand what the question really meant, but I guess I misunderstood it.
Yeah, I mean this is harder for sure because I'm asking you to create. You're basically like working this problem forward from scratch, whereas on the actual test you'll be given choices. But something that is given on the test is that they will make a dummy name, and it will be something like mystery gate or like what they call silly function. So it'll be some placeholder function, and I could have made it more clear that what we worked on here is called mystery gate, but this is very typical of a question. If you see the question set up some circuit and then later ask you to do something, it's probably related to the circuit that they just told you about. And this is complicated enough where they might even have one circuit and say, like, for the next 3 problems, we're going to ask about the circuit. So if you're ever left wondering, am I supposed to make something up, or almost never are you going to be asked to make something up on this test. That's probably like maybe a drawback on my approach is that in my approach,
Yeah,
you almost always should make something up. And in fact, if you had made something up, if you had made up some other circuit with 5 inputs like A, B, C, D, E, and you had solved it, like I would have been overjoyed. I would have given you like 105% with like extra credit and bonus points. But the test is not like that, unfortunately. So if you're ever asked to there's a missing gap where they're saying like do something to this like circuit, it's probably the one that they just told you about, like up above, usually with some stupid temporary sounding name. Okay, I'm gonna step away and get a drink of water. Why don't you switch over to the you can still have this on your screen, but switch over to the handbook on the same page with the Verilog, so it'll remind you what Verilog syntax looks like, and go ahead and write that module, and I'll be right back.
There is. Oh yeah. Ready? That not be let's see here.
All right, thanks for waiting. Where are we?
No worries. Hopefully I'm doing this right.
Oh, let me stop you there. So that on the handbook is an example of what Verilog looks like, but you are not. Oh, I see. Yeah, you're not a. Well, let's continue. But this is a different task than the one for number one. So I did tell you there were different equivalent forms, and I was asking you to translate from one to the other. And what I wanted to do was, given the circuit on the previous page, that's no longer displayed, but the one that was in the previous homework, go from that to something that looks like the Verilog. So, the circuit from there
Oh, okay.
was, like, something like that. And then I want you to write this. So this is the part I want you to write. But you're right. If you have something like this, you can translate it to be the circuit, and that could be another question as well. In fact, that'll be. You're already making good progress on it, so it'll be in the video. You can go back and copy it. So that'll be, new homework number one for this session will be to go in that direction. But so that was the direction that you were doing, and that's totally a valid direction. But the direction I'd like you to do for number one is this direction here. So circuits from the previous page, the one that we drew in red, that was
Yeah.
the tree and also the circuit graph, to write that in this form here in the box.
So you want me to? Okay,
Yeah.
gotcha. You just want me to write out the code.
Yes, which I know is like much harder because you have to learn basically a new language. You have to imitate what you see on this. I mean, the enormity of the whole like exam is basically like having you learn these deep concepts, but they present it to you in a very short space in the handbook. So it seems like it should be easy, but what they're asking you to do is actually, normally people can spend a whole quarter or semester learning Verilog. So so I understand if the task I'm asking you to do seems like hard,
No,
because it is, but
no.
doable, and you've been able to do it. So that's why. So maybe they're onto something. Maybe the NCEES people should be accelerating learning at college classes everywhere. Like, why spend a semester whenever Rob can do it in a few weeks? So,
Okay. So, um, no problem. It's gonna be
so I'll give you a few things. You can call it mystery gate. And so you'll begin. I'll just fill in here.
I mean, you just want me to write out just the Boolean formula, not the
No,
whole.
everything. The Boolean formula and the registered logic. So in order to remember what the registered logic looks like, you can
Yeah.
also look back at the previous screenshots to know what that looks like. But it contains, on if some edge of the clock signal But yeah, it'll be like this, some lines in the middle, and then end module. Yeah, so far so good. Okay, I'll erase this to get out of your way. Oops, hope I didn't accidentally erase some of your stuff.
No. And the code was A. Oh, well. Just for consistency's sake.
Yeah, you can uppercase them if you want.
I'll keep the output as lower. How's that look?
It's of the right form, and the plus, there's actually no plus for Boolean symbols, but what do you mean instead? So you have three basic combinational gates that you can use, and so I gave you them in the problem as well, and you used one of them. The ampersand is a
Oh,
and then the tilde is the not. So good, you picked up on that. Tilde means logical not,
wow.
but there's no plus. But yeah, right. Looks like you're replacing it with the or. So that's what. I mean, it is equivalent. Some places might use plus for or because 0 plus 1 is the same as 0 or 1, which is 1.
Yeah, where is that symbol? That or symbol that you use?
It's called the pipe. It's a vertical bar above the return key. So it's like the shift of the backslash key on most keyboards.
Oh, okay. Cool. Thanks.
Yeah, no problem.
Um,
Okay, let me
we
check.
haven't gone through the how to identify the reset and clock for that.
Well, we have. So if you look at the previous screenshot, there was like four multiple choices where I gave you examples of Verilog source code. Those exactly are examples of,
Mm.
on the left side of the screen where it says
Yeah,
A,
yeah.
B, C, D. So those are what you're meant to imitate. So those are clocked circuits, and you can keep the assign. The assign is used for asynchronous signals, and I'm going to make a slight tweak in that when you say assign Y, change that to assign Z because we're going to make up like a new wire that's internal to the circuit. And the Z is basically going to be the line that's between the AND gate, which is like three inputs, that goes to the register. So that will be Z, and then what comes out of the register will be Y. That's the output. So you can keep your assign statement, just call it assign Z, and then after that line, you're going to insert the clocked part of the circuit, which is going to be, the if some edge of the clock, and then that's going to handle the reset. And then there, instead of Q, you're going to assign to Y, and you're going to use the fat arrow, which is looks like the less than or equal to, but it's really a fat arrow of assignment. And before you do that, one slight correction, and that D and E actually go into a different gate, not just the OR gate, but a different kind of gate. So do you remember what gate that is?
Yeah, the exclusive OR.
Right. And I actually don't remember in Verilog how to do that, so I'm going to Google it. Briefly. Yeah, it looks like it's the caret, which is the shift above the 6, the number 6. That's XOR.
Is that right? The caret? Is that the caret?
That is the caret. Yeah. Good. I guess it kind of looks like a upside down caret pointed up or something, but.
If positive and it's going to be Is that right?
Well, yeah, but you did way more work. You repeated. So now you can assign directly to Y, which is that. Oh, yeah, so the output is still Y. When I said change to assign Z, you're just defining a new wire, but you still have the output called Y. And then in the circuit below, you can assign Z to Y in the else clause. But in the output, go ahead and change it back to output Y. And then in the if statements below, instead of assigning to Z, assign to Y. And then in the second time you assign to Y, you can just assign Z to Y. So this is a programming trick where you define it once, and then you can use the definition later. So because you define Z as this asynchronous signal up above, you can use it down below instead of having to retype the A and B or D exclusive for E or
Got you.
not C. So it's a lot faster. It's more maintainable. If you ever had to change the formula, you just change it at the line above. You don't have to change it in two
Like
places.
that.
Yes. Okay. You're done. That's it. Good job.
Okay.
100%. Full points for number one. Now we can. Any questions about this before we move on?
Nope.
Yeah.
Now that I practiced it, I think I understand it.
I probably could have put it in multiple choice form also, but your practice will pay off. You're able to solve like a sort of
Yeah.
a wide variety of problems now because you can create it going
Yeah,
forward.
I prefer this, at least for the time being. I prefer coming up with the answers from scratch. So thank you.
Yeah. And don't worry, you'll be able, when you're in a triage situation, you'll be able to sort of rule out two of the choices and then make a 50-50 guess. You'll be able to do that when the time comes. I believe in you. So let's move on to number two. You can screen share back to the homework from last time.
All right. Then it said, draw two timing waveforms, each with signals of clock reset. EN, I'm guessing EN is like enable.
Yep, that's right.
EN input Q demonstrating the difference between choice B and choice D.
So I'm talking about the choices A, B, C, D on the left-hand side.
Okay.
So now you have to understand the difference between these four choices. And I guess, yeah, you should try to see if you can see the difference and explain it in English first. And then that will help draw a timing waveform, which will show the difference.
Okay. Choice B says if a rising edge is clock, then if reset is high, then Q is appointed to 0. Else, Q will be appointed to enable and input versus choice D says if it's a rising edge clock, then reset is equal to 1. If reset is equal to 1, if reset is high, then Q will be equal to 0 or pointed to 0. Else, Q is going to be appointed enable and input exclusive or not enable and Q. Huh. And if.
Yeah. Okay. So first of all, how many lines are different between the two of them?
Just the L statement.
Right. Just one of them. So that narrows it down. They're pretty much essentially the same gate, except for the logic of Q when it's not being reset, which is most of the time.
Yeah.
And even the line that's different, what's the only part of the, like, what additional in D is missing from B?
Just the exclusive or, second half of that exclusive or.
Well, it's not. I guess maybe it is well, we could.
Oh, I'm sorry. That's just an or.
It's just an or, but I mean, this is like a review.
Yeah.
never miss the opportunity for a gratuitous review. So the review is this Boolean formula where you have A and B, or I guess you would write it A, B, or not A, C. Oh, that's why you're trying to add it, because when I first taught you or, it was using the plus sign. Okay, yeah. So my bad. It's just in Verilog. When you write it as a Boolean expression, people know what plus means between true and false. And in Verilog, I guess they don't let you do that. Their plus actually means between numbers, but the
And is
so
Verilog,
go ahead.
sorry, is Verilog just a coding methodology, or what's meant by Verilog?
It is a That's a good question. So it's in the section of your handbook under hardware description languages, HDL. So it is a way of, instead of drawing the circuit shapes and drawing lines between them, which is something that humans are good at, you can express them in code. And then once you express them in code, then computers are good at translating that. So then computers can produce the drawings that a human would draw, or a computer can analyze it for errors. It can do things like generate manufacturing drawings, like when you fabricate these gates in silicon at Intel's foundries, Intel or AMD or NVIDIA. NVIDIA is fabricating a lot of semiconductors lately for AI. But so whenever they fabricate it, they're doing it from this code. And when it's in code in text format, you can version it. You can put it in this service called GitHub. You can share it between people, so you can actually see what changes between the drawings. There's like a whole body of tools that are designed to work on plain text and sort of like the Unix software development way. And so that's the advantage of describing the circuit as code, but it is eventually going to be like hardware that's fabricated and that like runs electricity, and is going to be like sitting inside a box that you buy and bring home, and that heats up your lap whenever you do work on it.
Sure. Okay.
Good. So now you won't be curious whenever HDL shows up, like in the test, or whenever you look at the list of topics. You'll know when they say like HDL 12 questions. Like, okay, 12 questions will be about Verilog, which is a language that I definitely learned. Okay, so back to this Boolean identity. This I think is not exactly XOR, but it's similar. So this expression says A and B, or not A, C. And if we go back, this may have been like session
Wait,
3 or 4 or 5.
does that say C or not?
You basically have three variables, and then A is like the deciding factor between B and C. So this is the same as if you had an if statement in C. In Verilog it's also the same, but this is the same in C as if you say if A, then B, else C. So you can express that in a single expression by saying this. So this is equivalent. You can say like this is the declarative way of doing it, and there's some advantages. So declarative means also you can translate it to hardware, or that it runs in parallel, that all these things can be evaluated simultaneously, and you get a consistent answer. So if A is true, then what does this expression equal?
B.
That's it.
B.
That's it. Just B. Because if
Yeah.
A is true, then not A is false, and then the second part of this expression goes to false. And then true or false is just going to be true. So it's going to be whatever B is. Okay, and then if A is false, then what does the expression equal?
A is false, then it would be AC.
Well, if A is false, then not A is going to be what?
C.
Not A is going to be true. So again, if in doubt and you're given a Boolean expression, you can draw the truth table for it, including any intermediate expressions that you want to figure out. So you can label the columns A, B, C. You can label not A. You can label A, B. You can label not A, C. And then you can also label the output. They got stretched. Let me try that again. Yeah, Zoom's drawing could use a lot of work. Okay, so go ahead and fill in this truth table, which you know how to do because there are 3 variables. So how many rows does this truth table have?
8.
Right, 2 to the third is 8. So go ahead and write out all the rows, which include the values of A, B, and C in a canonical order. So there's good. So far, so good.
Okay.
Great. So I guess let's verify. So for the first half of the table, A is false. Well, let's do the bottom half. So the bottom half of the table, A is true. And if you look at this, what we discussed, if A is true, then the expression is just going to be equal to B. So just verify and go over here to the output column, and is it the case for this lower half that the output is just going to follow whatever B is? Yeah, 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 yeah. So, is it the same? Yes? No?
Yes. Yeah. Oh, I'm shaking my head. Sorry. Yeah.
Okay. Okay. I thought you were, but it's too subtle to tell. Okay. Now, for the top half of the table, when A is false, is it always going to be the case that the output is C?
Yeah.
Yeah. Okay. So they're equivalent. So again, this is letting us practice. This is a very early concept for us, but we had a Boolean logic expression, we had a truth table, and then now if I asked you to draw the gates, you could do it too. So good. Now we'll practice with. I will give you a multiple choice question now, which is, this is not quite XOR, but if it were, well, I'll mute and let me come up with some choices, and then I'll draw them. Okay, so here are your choices. The question is, if you were to make only two changes to the previous formula in order to make it equal the definition of A XOR B, which of the following choices shows the two changes you would make. So it's a little hard to read. Let me move it up here. And then let me give some text labels. Okay, so you have this formula here. We studied it for a while. We drew the truth table. It's not exactly A XOR B, but it can be made A XOR B with two changes. And by change, I mean you can change symbol names. You can change any of the A, B, or C to another C, B, or A. You can change any of the operators. So if you see an and, or, not, or ampersand, plus sign, exclamation point, you can change them to any of the other signs. So those are the changes you can make. And with only two changes, you can make it equal to an expression that is the same as A XOR B. And so the question is, which of these four choices shows you the two changes that you would make?
Okay.
Yeah.
So there's a number of ways you can do it, I guess.
Yeah. That's a good question. If there's more than one way to do it.
Yeah. So what I would personally do is first look and see what A XOR B would look like, I guess. So let me write it out. I'll put it over here. So B would be zero, zero. Zero, zero. So that's what it would look like for me.
Mm-hmm. Okay.
Then I would see if I could find a pattern or similarity there. 0, 0, 1, 1. Okay. So to change it from A, B, or not A and C. So A, B. So I can eliminate C because that's more than two changes. A, B plus A, not B. So I can eliminate that. I can eliminate B. So it's A, not B. Oh, it's A.
That's right. I really threw you off because I'm putting it first.
Well, I was just working up the.
You did it the right way. No, absolutely. You're not going to get fooled. You exactly picked it. And you can, now you might recognize it. Like you might be able to pick it off just because you're like, oh, that one looks right because I remember it. But but if you did it, you worked it out the right way. And if you had to knock out one of these, it's just a test taking tactic. Like if you had to eliminate one right off the bat, which one could you eliminate?
It was the one that had more than two changes. I think it was C.
Did that one have more than two changes? Oh, you're right. Oh, well, that was my bad. Okay, good. Then if you had to eliminate another one, right after that one, what would you do?
Um,
Which one would it be?
Probably B.
That's right. So what looks suspicious about B?
Um, you just made it not C, so it's C.
Well, you want the expression A XOR B, and you don't need C at all at that point. So that's why that choice isn't needed. But good. And then D is also interesting. How would you write D in a shorter way? Is there a shorter way to write D?
Yeah. If I remember correctly, it's like a property, a Boolean property. And if you have basically it equals one, right? Because you have A plus not A. Same thing as AB plus not AB. Not A, not B. I believe it's just equal to one.
Well, I don't. Something like that might be true, but I don't know how to apply it in this case. I guess there are a couple of ways which are also good to review. I'm only like this is a little. This not, has nothing to do with Verilog. I'm digging into it now just because it's practice test time's coming up. You're definitely more than ready. I'm just like inching you from 50% to 51%
Sure.
of the line. So if we were to what was I going to say? So if we were to use De Morgan's theorem, do you remember these De Morgan's theorems? It's ways of transforming an expression, and there are two of them. So it may be on your cheat sheet. Let's look in the learning log. There's a it's not. Let me add it then. Yeah, actually, we should probably spend maybe the next lesson on filling out the cheat sheet. And I know you've been keeping notes. You may already have your own cheat sheet, but we'll construct things that I think are useful. We'll combine all of them into one cheat sheet. But so De Morgan's theorems, I'm just going to add it to. It's on page 78. So 78. Oh, that's substantial. We've been doing a ton of work. That's like satisfying to see. So De Morgan's theorems have two forms. One is if you take like the double negation of, if you negate an or, that's the same as taking an and of their negations. And then if you negate an and, that's the same as taking an or of their negations. And so sometimes you can apply this with a double negation. So, if you have some expression C or like Z, sometimes you can, and that's equivalent just like double negation of Z. So if you have something you want to simplify, like, like A or B or not A, not B, you can take a double negation and then use De Morgan's on one level. So split apart the negations to just work on the intermediate half here. And we're going to get some more water. This will be the last thing we do today, but try working on that. Simplify it if you can using De Morgan's, and I'll be right back.
Decide what you want. I I asked you a question as you walked out.
Oh,
Uh,
what's up?
which problem am I applying the De Morgan's theorem to?
Well, I wrote it. I guess it's not really technically part of the cheat sheet, but
Oh,
it's converting. So the question is this expression, which was
it's okay if I.
one of the wrong choices, D, like on the yeah. So choice D, where it says A B, or not A, not B. So can you simplify that expression further using De Morgan's? And so a clue was that you can double negate it. You can just like wrap the whole thing in parentheses, put a bang bang at the beginning, and then concentrate on just the inner bang, and then simplify that, and then keep the outer bang in case you need it.
You're okay if I know I'm screen sharing, but you're okay if I scroll to that page.
Yeah, that's fine. Yeah, let me take a screenshot of.
Well, you want me to go back?
Uh,
There you go.
oh, good. Thank you. Okay, now you can scroll, please.
All right, here you go. So I can just write it in different stages, I guess.
Yep. However you want to solve the problem, it's up to your creative direction.
Sure. Yeah.
So which of De Morgan's theorems did you apply? The
The first theorem and the second theorem.
Okay, so the first one you
I distributed this first knot
okay,
to the.
that is a good instinct, but you unfortunately you cannot distribute it. So if you mean to distribute it to not A B, this is not the same as not A, not B. But it was a good start. So you did change the or to an and, but then you want to take a knot of both sides. You just have to be sure that you are taking a knot of the whole expression, and that, for example, the knot of both. Yeah, so again, if you take the knot of parentheses, not A, not B, that's not the same as just AB. So you got to rework that part.
Oh, okay.
In a sense, you have to apply De Morgan's a second time to figure out what that is. Because AB is short for A and B.
Oh,
Just like not A, not B is short
gotcha,
for
gotcha.
not A and not B.
Yes,
Okay, you got it now.
yes.
Good. Extra De Morgan's practice. It was baked in. Actually, there'll be a third. You have to apply it to Morgan's a third time. No, I'm kidding. It's just the second time.
How's that look?
Yeah, I would have to think pretty hard to come up with that one. So.
How's that look?
Will you? I'm not sure I understand it. Okay, so you have
So I had A and B
So now you have not A or
not B.
not B and
Well, it's
A,
not.
A or B. Um, okay,
Yeah.
so then I don't get how you made this jump.
So if I distribute out the not, it would be here. Let me clean this up and make it look nicer. That way,
Okay,
maybe. Um.
but what I've written next to yours is what it simplifies out to, and then you also have the outer bang that we haven't used yet, which is fine because you can
Yeah.
simplify. You can simplify the inner expression.
Okay. So I did the first distribution. A is going to be not A, and is going to change to or. B is going to change to not B. A or is going to change to and. Not A is going to change to A, and is going to change to or, not B. Okay. Distributing it out. The next one, A, not A is going to be A, or is now going to be and. Not B is going to be B, and is not going to be or. Let me put that one as not A, or is going to change to and. B is going to change to not B. Does that look better?
Yeah, well, it's equivalent, and but it's still. But I don't get how you are. You basically ended up where you started, which is which was not the goal.
Oh,
It's kind
I
of
thought I thought that was the point of the double bangs, but
well, you're. I mean, it is all equivalent for sure. It's but there's another step. So it's kind of like you're in a car and you're going to Disneyland, and at every step along the way, you're with your family, and at the very next to last step before you get to Disneyland, you could turn around and go home, and you're still all together. And in some ways, it's equivalent because you're like, well, if we got home from Disneyland, there'd still be the four of us, and we'd still be in a car and wearing these clothes or something. But you would have missed out on going to Disneyland, so it's not quite equivalent. But all the expressions are the same. I agree. But the reason for taking the trip is to get to Disneyland. So let me show you what. And this is a pale comparison. Obviously, solving this Boolean expression is not the same as going to Disneyland, but especially not to your kids. If you ask them, so there is a turn you could have made to keep going further. But it is important. It is true that every step along the way is equivalent. You can close the circle and get back to z at the end. So the question is, how do you simplify this expression here? And that question is, how do you distribute the and sign?
okay.
So I guess we'll maybe on a cheat sheet we should have Boolean identities. Oh man. Well, I'll tell you what to type. You can type this part. It's so go ahead and press enter a few times and then type Boolean identities. And the first Boolean identity will be A, open parentheses A, or B, with a plus sign, close parentheses, and then C, which is the same as and C. Yeah, equals AC or BC. Okay, so I'll add one more as well. Just this one is sort of related to anything with an and you can flip. There's like a symmetric property, but you can also say something like C and open parentheses. This is a whole new expression. So C and open parentheses A or B equals and it's also the same thing. Yeah, you can say CA or CB, but then you can also say equals. You can add another equals, and you can say AC or BC. So all those expressions are the same. So that's to say that you can distribute the and operation over an or, and even if the and is after the or the and comes before the or, it doesn't matter. So you can do it both ways. So, but we'll stop there, and I'll give you 3 homework problems, and the first homework problem will be to continue the circuit translation that you started, and you can watch the video to remind yourself which one that was. But on page 206 at the top, it would be to draw the asynchronous circuit, or sequential or combinational or unclocked. So draw the unclocked circuit relating the inputs A, B, C to the output Y in the Verilog module silly function. So I'll type that in session 17. Yeah, this is what I should be doing all along to make it nice and neat. I've just been cheating by putting in the screenshots and making you work harder by watching the videos. So,
and we never answered number 3 from last week.
What is number 3 from last week?
There was a number 3 question.
Oh, okay. So draw the asynchronous circuit relating inputs A, B, C to the output Y in the Verilog module silly function on the handbook page 206. And the number 2 is finish simplifying A, B, or not A, not B. Using De Morgan's and distributive identities. And then what was number 3 from last time?
On page 119, how many address bits does the read-only memory have? How many data bits? And draw the read-only memory as a table with 2 columns. For every address, write the data stored.
Well, we can do it now. Do you?
Yeah, let's do it.
Okay. What is it? How many address bits are in this ROM? It's still a memory. You know, they tell you that you can't write into it, but that doesn't affect how big it is.
Yeah. Um. So so it says W8, but word address. I want to say 3 bits.
Why do you say 3 bits?
Well, if you can see these, there's 3 bits right there at the top. It says
Oh,
word is 3, and it goes from 1 to 8 right here.
yeah, you're right.
But
Okay. I was
if I
being
do
te-
log 8,
I was being testy, but that's exactly right. So
oh, okay. All right.
good. Part B. How many data bits are there?
4.
That's right. Can you show them to me? Are they the columns or the rows?
Oh, the rows.
Yeah, that's right. So for every address, all the 8 addresses, there are different 4 intersections, 4 bits that can be stored. They can vary independently. That's where those little fuses are
Oh,
drawn. And
so what do those fuses mean?
well, those are not fuses. Those are switches or transistors. So they one end is their MOSFET. So the end coming in with like the little plate drawn at the top, that's the gate. So whenever it is high, it's going to short the two other ends, which is called the drain and the source together. And the source is a ground, and so that's a 0. And then the other side, the drain, is going to be the address line. So if the transistor is there, and then that address is a 1 that gets raised high, that means it's going to short that bit to ground. So it's going to pull it down to 0. And so it's kind of the opposite of what you might expect. Sometimes you think in a memory that you record the ones, but no, in this case you record the zeros, and then, well, yeah. So you record the zeros.
Okay.
So if the transistor is there, it's a 0, and then when you read out the line at the bottom, and it has this transistor with a gate tied to its source, which is, what does that mean? That means it's they're permanently shorted, so it would be inactive unless it were raised to a 1, and then yeah, I'm not sure why there are MOSFETs on the output, but it doesn't change the.
Are you talking about these ones over here?
Yeah. I think those are done as like power amplifiers. Like those are so that the whatever is consuming the memory isn't going to like draw too much current or like short out the memory chip itself. I think those are just drivers. But yeah, so the
I think
memory. Go
is
ahead.
isn't that indicating that those are active bits, that they're not like dead bits per se? Because like, are there ever time? And I'm just going off of memory from when I was in school, but aren't there ever times where you can have like let's say a 3 bit word address, but then you can have more output addresses, and the MOSFET would show which ones are active.
Well, the MOSFETs in the middle at the grid intersections do show you which bits are 0 when the memory was written.
Yeah,
But then the MOSFETs at the
and
end, they're there no matter what. So all the bits have them. So there's nothing to differentiate between them,
oh,
and
okay.
they're all used. Otherwise, your memory has a data bit that doesn't work. So you paid for 4 data bits and you want all of them to work. So I think that at the end is just a detail of amplifying the signal, but just because it's there doesn't mean you have to understand all the
Got
details. There's like a lot of details in this handbook which we've skipped over. So okay, so good. So part C is draw the contents of the ROM. As a typical memory, two columns, address and data, and now that you know the transistor is there, it means like for that bit, for that address, it's a 0, and if the transistor's not there, then it's a 1. So if you can do that in the next few minutes, then we'll wrap up this problem.
So you just want to draw the table then?
Yep. It's what I've trained you your whole life to be good at. It's drawing tables, reading tables, tabling tables, anything with tables. You got it.
Okay, I did not do that right.
It's okay. We've got lots of minutes.
Yeah. Oh.
Oh, it's a lot of bits. Oh, you're writing them out from left to right. I was thinking of a typical memory that I've drawn for you and asked you to draw for me is the address bits, of which you've said there are 4. So in the first column, it would just be all 4-bit addresses, and then next to it would be the data stored. So you kind of have to rotate the table in your mind and then write it out. You're writing out the bits like as they are in the table, but that's not like all the other tables that we've looked at in our lesson so far. Yeah, well, good. This is really forcing you to understand the address now. So even when it's rotated 90 degrees, you still got to know what's going on. So how many address bits are there?
3.
Oh, that's right. There are 3. Okay, so how many rows does this table have?
8.
Right. So write all the 8 3-bit addresses in the right order. 002. You're really going to try and sneak that by me. Nice try.
Yeah.
Okay, so then that's one column. The column next to it will be data. So then write how many data bits are there?
4.
Right. So next to each 3-bit address, you got to write 4 data bits that are stored at that address.
Yeah, this is gonna be good practice. I'm trying to remember how to do that. It was
So you're trying to write them horizontally before like all the data bits, but instead you should rotate them 90 degrees and then write them on a per row basis instead of writing one column first and then the second column. Like you were trying to write like all the least significant bits first for all the addresses, and then all the next to least significant bits, like all the B0s, all the B1s first, all the B2s, and then all the B4s. But that's not the most useful form for a memory. So So just read down each column.
Going to be
Oh, and be sure that you're writing them from most significant to least significant bit. So you would be writing it from B3 to B0. Yeah. But other than that, you're doing it right. Oh, you were doing it right. Yeah, never mind. Don't listen to me. So
Are you just trying to trick me there, huh?
I wasn't trying to trick you. I was wrong. Yeah.
No,
Yeah.
I was just joking.
Yeah. Nice. You got it. Yeah, I know that was a lot to keep in your head. It's very mind bending, even for me to follow it. But yeah, but now memories are super easy. You got this problem, and you can answer lots of questions about it. So good. Number 3 done. Check mark.
Oh,
Gold star. Now I have to give you a new number 3 for homework. So it will be on data structures, which is more of a software engineering. Yeah, I probably should have done this earlier, like just giving you sections to read, but I never fully trusted the handbook as like covering everything you needed in the text, which I probably should have more because some of the text is pretty good. Let me find something about data structures. I'm going to search. Yeah, well, we won't make it too involved. So there's on page 168, there's a section on software testing. So I just want you to read it, and then
software testing.
yeah, on page 168.
Okay.
Yeah. Well, it's going to be a little harder because it's like a creation test, but it'll be good. It's so read page 168 on software testing in the handbook. Then choose one and write out and draw out a timing waveform diagram like we've been drawing for the clocked circuits. So demonstrating that kind of test for the silly function module that we've been studying on page 206. So there are 4 kinds of tests. And it's kind of a more flexible question because you can choose whatever kind of test that you think you understand the best. And then any kind of timing waveform diagram will be a test because you're going to be writing what you expect to be the output. And then you're also going to give it the kinds of inputs that are useful to produce the output. So I'll tell you the silly function module has signals A, B, and C, and then the output Y. Yeah, so we've been studying like timing waveforms for clocked circuits, but this one doesn't have a clock. But you can space out which sections you want to demonstrate. Yeah, I guess I'll give you I'll give you an example of that. So in a normal timing diagram, one of the signals would be called a clock, and it would like bump along at a regular clock rate. But in this case, there is no clock. You're just going to draw a bunch of signals and label them, and then you're going to choose. You'll just like space apart different time steps, like, as if pretend that there was a clock. There isn't, but just pretend like you're spacing them out far enough where the circuit would have time to settle. And then you're going to give some inputs. Like, let's say for the first one, you choose an input of A is 1, B is 0, C is 1. And then down here, you would draw whatever it is that you expect Y to be. So I've even forgotten what the expression was, but that's good because I can't bias you one way or the other. So you got to figure out what Y would be for that input and then draw the expected 1. And maybe for the second time step, the pseudo time step, you set B to 1 and A to 1 and C to 0, and then again, Y has some expected output. So, this is a test where if you only know the formula for the module or the function or the circuit, or even if you don't know it, you can just give this test to someone and say, like, make me a Verilog function that meets this test, that passes this test. And they could probably do it. And the trick here is that if you were to draw this out for 8 time steps, like all 8 possible combinations, then for sure they could do it, no problem. But let's say that you only had 4 time steps. So like how would you choose 4 test cases? So each of these is a test case. How would you choose the 4 test cases and the correct outputs for Y such that someone would know exactly which function you're trying to specify? So you don't want it to over specify or under specify. So those terms in tests mean if you over specify, that would be like if you sent them a test with like 16 test cases, then someone would have said, like, that's overkill. Like this, there are only 8 possible inputs, and you gave me you basically repeated yourself. You duplicated some examples. So you gave me like 16 examples for a circuit which can only have 8 different possible inputs. So that's called overspecifying. And when you overspecify, what's even worse is that you can make a mistake and then you could like contradict yourself. You could say, ABC is 101 should produce a Y that is 0 here, but then later you said it should produce 1. So if you repeat yourself, there's a chance that it'll be inconsistent. So, and it's also inefficient. So that's the problem with overspecifying. If it's underspecifying, it means that you didn't give enough inputs, and sometimes that may be vague. That means like multiple circuits could satisfy this test. So your job is just to choose 4 examples and be able to justify why, and then also to say whether it's underspecified or whether it's enough to specify the function.
Okay.
Okay, and then for homework 4 is we didn't finish. We didn't finish the question of what is the what was it? It was we didn't finish question 2 either. So question 2 said, from last night, said draw 2 timing waveforms, each with the signals clock, reset, EN, input, Q, demonstrating the difference between choice B and D. So that one still we need to do.
Yeah, we just discussed. I didn't draw it out, did I?
Well, we went on a tangent to sort of simplify the expression because, well, for that one, so draw 2 timing diagrams for choices B and D, which differ only in one line, to show the difference between them. So one of them was Q gets assigned EN and input, and then the other one, Q gets assigned EN and input, or not EN and the previous value Q. So so definitely review this video, which hopefully should be available a few minutes afterwards. No separate upload needed. And so we talked about the key expression that we talked about is this, A, B, or not A, C. Remember that we spent a long time on that. So that expression has a meaning, and then instead of A, B, and C, now you should apply that to, enable and the current input, or not enable and the previous value or the current value. So this Q is a registered circuit, so it holds a value. It can be reset to 0. It can be taken from the input if it's an enabled, or it can just hold its previous value if it's not enabled. And that's basically what this expression means. So you would be taking enable as like A in that example, the input, the new desired input would be B, and then the previous Q, the previous value, would be C. So however you want to make sense of that, draw 2 timing diagrams and choose inputs just like you chose inputs in problem 3, and then show what the corresponding output, what the expected Q would be. So in a sense, you're writing tests for 4 too. So 3 and 4 about testing. Okay, I know that may still be vague, but good. You do your best work under vagueness. I think if it's like too clearly spelled out, then you'll get bored and you'll grow soft and you won't be ready for the test. So, but you will be ready for the test. You're in good shape. This is just more muscle, strong finish.
Yeah, yeah, I don't mind it. Um, so we're meeting Friday and then Saturday again, right?
Yes, yes. Are you up for it?
Yeah. Um, or do you think it's better that we meet Thursday so that it's like every other day versus Friday and Saturday?
I actually do think Thursday would be better. So I'm free if you're free, and then you can get an early night's sleep on Friday, or as much as that's possible with kids and everything else. But
Yeah, that was kind of my thought process. So yeah, I would prefer meeting Thursday if you can.
good. Maybe even the calendar appointment ran out. But let's meet Thursday, June 8th at 6. And then on Saturday, June 10th. That's when you're expecting, right?
Yeah. And what time Saturday?
As close to the real exam time as possible. So if they start at 8 a.m., we should start at 8 a.m. If they start at 8:30, we should start at 8:30. And then I'm happy to read you the disclaimer and play the part of the typical exam proctor. Do you have that information anywhere?
The proctor or the
The times, I mean. If not, I can look it up.
I have it. Let me pull it out.
Yeah, no worries. Yeah, I
It's
don't know.
at 8.
It's at 8 a.m.
Yeah, which would be 9 o'clock your time?
Wait, are you in Central Time?
Yeah.
Oh, okay. This whole time I didn't know. Okay, so 8 to 9 practice exam start, and I was just reading on the website that it said the exam was 6 hours, not 8 hours.
Which exam
The electrical and computer.
is 6 hours?
Let me send you the link.
Actually, the
I'm
computer engineering exam is 8.5 hours. It's
okay.
actually a 9, I believe.
Maybe I'm
Nine and a
looking.
half.
Maybe the one I'm looking at is wrong then.
Yeah. Actually, here, let me show it to you. I have it up. So it says, but 8.5 for the exam, 50-minute schedule break.
Yeah, mine is for 2020, so maybe they changed it. You're right. Just 8.5. Okay, so let's do 4 in the morning. So 8 a.m. your time to 12 noon. We'll add in the 10 minutes of tutorial and non-disclosure agreement. So to 12 noon, and then a scheduled break 50 minutes. So at 12:50, we can call it like 1 p.m. your time. We resume for another 4 minutes, 4 hours until 5 p.m. So
So we're gonna go 8 to noon and then
1
1.
to 5.
You mean 5:30?
Oh, you're right. There's a half hour. So yes, the time will be available. Feel free to use it. You have all the time in the world, but also if you finish early, it's also acceptable. So
So should I print off the practice test that morning then, I guess? Now, maybe we'll do that the first 10 minutes.
yeah, definitely have a printer ready, and if you can come into the office so you can concentrate on it, that would be great. I'm just gonna send you some calendar appointments. You're gonna get a bunch of appointments for me, so just what they are. Just make sure that the times look right to you. Let's. I think I got the.
Um, just for consistency's sake,
Yeah.
uh, I guess we'll do 40 questions in the morning, 45 in the afternoon.
Yeah, unless
'Cause-
on the real exam, would they let you do it all? Like, if you get it all done in the morning, would they let you do it, or they'd only give you half of the questions?
So yeah, they only give you uh, half the question. So either I'll get 40 or 45 questions in the morning, and then if I get 45, I get 4.5 hours. And then once I hit that time limit, what they do is, let's say I finish the 45 questions in 3 hours, I get an extra hour and a half in the afternoon. So I could either choose to take my break right then and say, hey, I'm taking my break now. And I can't go back to those 45 questions that I did in the morning. And I get an extra hour and a half in the afternoon.
That sounds pretty complicated. So okay, so you're not allowed to check. So you can choose. Do they choose, or do you choose whether you get 45 questions in the
No,
morning or?
yeah, they technically, I guess they do, but it's literally just system generated. Some people will get the 45 in the morning, some people will get the 40.
So you won't. So you may take breaks at different times, is what you're saying. Like some people.
So, so yeah, basically what they do is when we come in and take the exam, the first 10 minutes they'll go over everything. And then the second I say ready to take the exam, I hit that button, the exam generates, and either I'll get the 40 or 45 questions.
They
And
generate the exam. Sorry to interrupt. Like right there, like when you show up that day.
yeah, like it's computer generated. And they
Okay.
Yeah, so basically like the second they second I hit that button, they have a database of how many ever questions that they populate, and it generates literally that second.
Does everyone get different questions?
Yeah.
This sounds wild. Oh my god, these people have it down, man. Okay, now I actually want to work for these people. Before I thought like test taking was like totally lame and like not real engineering work, but they've thought about this. Like you can't game the system, and they're having you sign a non-disclosure saying that you probably won't reveal what the questions are to anyone. And
Yeah,
yeah,
there's really no way to get they check your fingerprints when you get there. They
yeah.
they do all kinds of crazy stuff to make sure it's not someone else taking the exam for you, and it's pretty intense.
Well, on the plus side, after this, you can design a bridge that will fall down. And but you're a computer engineer, so
Yeah, right?
yeah. Okay. Well, that's really sophisticated. So okay. Well, that little bit of flexibility, but we'll make it as realistic as we can. I feel good. I think we can do it. I think we can get you in the mindset. And again, we only expect you to get like 50% of the questions. I mean, of course, you can do more. I believe in you, but that's the feeling you should look out for anyway. The expectation going in.
Okay.
Yeah. Okay. Well, good work today, Rob. I know I kept you late. I know the video was delayed, but I'm going to actually stop the stream right now.